Okay, so why we use transition metals in um, organic transformation? Because as we can see over here in this table, each transition metal in first series, scandium, titanium, iridium, chromium, manganese, cobalt, nickel, copper, zinc. In that one, you can see almost all transition metals they do show different oxygen states. That means here I have written that transition metals they do change their oxygen state in situ. Okay, that means in between the reaction they do change their oxidation states, and scientists took benefits of these all these beautiful property of these transition metals, and they did use these things in organic transformation. So that's why we can carry out the coupling reaction with the help of this transition metal catalyst. Okay, so cross coupling reactions, as we have seen cross coupling reaction. In cross coupling reactions, uh, different steps involved. Okay, so out of those steps, four different steps, four important steps involved. Out of that one, oxidative addition and reductive elimination, these two steps are very important. Oxidative addition step is the first step which occurs in reactions, in coupling reactions, and reductive elimination is the last step which occurs in each and every coupling reaction. Okay, so any reaction, Suzuki coupling, Suzuki cross coupling, Heck coupling reaction, Negishi, Fukuyama, Kumada. In any reaction, you can find oxidative addition is the first step of the reaction and reductive elimination the last step. So oxidative addition and reductive elimination are reaction pairs that involves a change in the oxygen state and coordination number of the metal. So in oxidative addition and reductive elimination, here only the transition metals they do change their oxidation states and their coordination number. Okay, and in oxidation state, if the oxidation state is increased by +1, and the same thing, that means if oxidation state is increased, that oxidation state is decreasing in reductive elimination. That means total net effect of the transition state of that metal is equal to whatever we have started, that is the that oxidation state of that transition metal we can find at last stage of the finishing of the reaction by oxidative addition and reductive. They are compensating the oxidation state of their that metal, oxidative addition and reductive elimination. In oxidative addition, increase in the oxygen state and coordination number of the metal. Okay, so oxidative addition, in oxidation addition step, the oxidation state as well as coordination number of the metal, transition metal is increasing by increasing. Meanwhile, in reductive elimination, Okay, the reductive that the increased coordination number of oxygen state, that one is decreasing. Also, coordination number is also decreasing of that particular metal. These two reactions occurs through sigma bond and can be described schematically by the following reaction. Let's see whether I have dropped. Okay, I have written over here the reaction. So here you can say how what is the oxidative addition of element metal. So here is we have taken the palladium is in zero oxygen state, and here we have taken aryl halide as a starting material. So how is the oxidative addition? That means now palladium we have to add in between this carbon atom and this halide atom. Okay, that means in between these two we have to add. So what we have started addition of palladium, and now palladium 0 is transformed into the palladium second when that one is getting added in between carbon and halogen. Okay, so we have formed new bond in between carbon palladium and palladium halide bond. Okay, so this is nothing but the oxidative addition of aryl halide. Okay, so aryl halide oxidative addition aryl halide to the palladium, and like that we can say. Okay, so unique reactions in organometallic chemistry. These coupling reactions are unique reactions in organometallic chemistry. So as I have said, 4 different steps involved. So out of that one, we have seen oxidative addition and reactive elimination. The next 2 steps are migratory insertion and beta hydrogen elimination. Okay, these 2 steps are also very important in coupling reactions. So these first 2 steps definitely you can find in each and every coupling reaction. These two remaining 2 steps you can find in some reaction, or you cannot find in some of the remaining reaction. Oxidative addition, let's have a look. Maybe you have studied Wilkinson's catalyst reaction. Okay, Wilkinson at first MSc first year. So that one is also included the same mechanism, oxidative addition as well as reductive elimination. So when addition of ligands, okay, ligand, these are the ligands, pph3 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 chlorine. Okay, these are the ligands which is attached to the central metal atom. This is metal, and these are the ligands which are attached to this metal. Okay, when addition of ligands is accompanied by oxidation of the metal, it is called oxidative addition reaction. Now here we are going to see how the H2 add oxidative via oxidative addition pathway to this rhodium. Rhodium is now in +1 oxidation state. Okay, so here is the example of what is the oxidative addition. Very nicely they have explained. This is Wilkinson's catalyst, and we are going to add H2 to this rhodium. Okay, so rhodium should have at least some empty space to acquire this H2 hydrogen atom. Okay, so rhodium should have empty spaces. So here you can pay attention, rhodium is in +1 oxidation state. That means rhodium has empty space or empty orbital to accommodate these 2 hydrogen atoms. So here you can see 2 hydrogen atom is getting added to this rhodium. Okay, so you can find now rhodium, 2 rhodium hydrogen bond has been formed in this structure, and as this 2 rhodium hydrogen bond has formed, the oxygen state of rhodium is now +3. Okay, so this is oxidative addition. Oxygen state changes from +1 to +3. So oxygen state of metal increased by 2 units. Coordination number of metal is also increased by 2 units. 2 new anionic ligands are added to the metal. Okay, so in first thing we have only 4 ligands attached to the rhodium. Now in second, after addition of this H2, you can find rhodium has now total 6 ligands on this rhodium metal. Next one, requirement for the oxidative addition. Okay, availability of the non-bonded electron density on the metal. Okay, 2 vacant coordination site on the reacting complex. That is, the complex must be coordinatively unsaturated. A metal with stable oxygen state separated by 2 units. The higher oxygen state must be energetically accessible and stable. So overall, what are the requirements for oxygen status? Oxidation addition, that rhodium should have empty space. If here rhodium is in +4 oxygen state, for example, if rhodium is in +4 oxygen state, then we cannot add this H2 to this rhodium. Okay, so rhodium should be at first stage of this reaction. Any element, any transition metal should be in lowest oxygen state, 0 or +1. Okay, so if you take +3 or +4 oxidative addition is getting difficult. It's not that of easy. So rhodium should have empty space on that proper metal, any transition metals what you are going to use. So here hydrogenation of alkenes, Wilkinson's catalyst. Okay, so this reaction is very popular. So rhodium first, the same thing, rhodium first changed to rhodium plus 3 by oxidative addition of these two hydrogen atoms. Then they have given all these reaction in, okay, Cativa process also. Cativa, here is a Suzuki coupling. In Suzuki coupling, they have used palladium, diphenylphosphine, tris triphenylphosphine. Okay, these two ligands of tris triphenylphosphine, they are present on palladium. Palladium is in zero oxygen state, and that one is this one is getting added. That means aryl bromide is getting added to this palladium. Okay, so here they have shown the addition of bromine and aromatic ring. Okay, and now palladium oxygen state is changed by +2. So this is oxidative addition reaction. Here also you can find in Cativa process. This is also one process. In Cativa process, again transition metals they have used iridium. They have taken iridium with 4 different ligands having +1 oxygen state. We have added another, we want to add another oxidative addition of methyl iodide we want to do. So here we have done oxidative addition of methyl iodide, but after addition, after formation of new iridium carbon bond, iridium iodine bond, iridium oxygen state of iridium plus change from +1 to +3. So this is nothing but the more electron reach the metal, the more easy is the oxidative addition. That means here you can see palladium is in zero oxygen. That means palladium possess all its electronic configuration is still as it is. There is no loss of any electron from the original electron configuration of palladium. So that's why electron metal is electron rich, and as that metal is electron, it can give its electron to another ligand. Okay, it can share its electron to another ligand. So here palladium shared 2 electrons with 2 different ligands to form this bond, and that's why now oxidation state is +2. Okay, this is the oxidation state, oxidative addition reaction to the transition metal. Now next, what is the reductive elimination? Okay, next step is reductive elimination. That one is exactly reverse to the oxidative addition. Okay, so what we have to do, whatever mm, oxygen state whatever has been changed or +4. Okay, so now platinum lost 4 electrons. Okay, platinum has given 4 electrons to different or ligands. Okay, so now he will acquire again these ligands by reductive elimination. Okay, by elimination of 2 methyl group. Okay, this 2 methyl they have removed from this platinum, and in that way this methyl group donated their one electron to this platinum. Now oxygen state is +2, platinum +2. So this is the reductive elimination, and so we can synthesize, or we have created new carbon carbon single bond in between two carbon sp3 hybridized carbon atom with the help of this platinum transition metal catalyst. Okay, so as platinum can change its oxygen state in between the reaction, that's why this is possible to create new carbon carbon single bond. Oxidation state of metal decreased by 2 unit in reductive elimination. Coordination number decreased by 2 unit in reductive elimination. Two cis-oriented ionic ligands form stable sigma bond and leave the metal. Okay, so factors that facilitate reductive elimination: a high formal positive charge on the metal. This should be the high formal positive charge. The presence of bulky groups on the metal. Okay, bulky groups should be the on the metal. There here are bulky groups, and an electronically stable organic product. Okay, these are the requirement. Cis orientation. Okay, this is important. Cis orientation of the groups taking part in the reductive elimination is a must. That we will see what is the cis orientation. Everything we will see in our coming lecture. There are a lot of things still we have to explain in this case of the oxidative addition and reductive elimination topic. Okay, so